Now that we studied the digital comparator and the flash ADC converter, let's just mention one circuit, but without studying it fully, because it requires, let's say, some time, a lot of time. So it's the so-called analog adder circuit. So this circuit you see here in this panel. So this is the circuit that we can use when we want to compute the summation of analog signals. So by summation I mean that if we have a signal like this, for instance, and another signal like this one, so if I put them on a graph and point by point I add the values of those two signals, then the result will be something like this, and so on. So analog summation. This thing can be useful also for implementing the summation node of a neural network implemented with operational amplifiers. So we don't study all this, but the result is described by this equation here, where it tells you that the output is the summation of the input signals multiplied by some weights. Sorry, actually X are the weights, V is the voltage, and we have voltages applied to the minus and to the plus input, so the voltages can be summated or subtracted, so the weights can be positive or negatives. So this gives you an idea that if you have a differential amplifier, you can create a summating nodes having positive and zero and negative weights. So with this you will be able to reconstruct the logic gates that we have studied a while ago. So I want to mention one thing about circuits. So electronics is full of circuits. So every circuit needs to be demonstrated. It means that you can't easily understand a circuit like this if you don't pass through all the calculations. The bigger the circuits, the more difficult to be calculated. So for this reason, it's a good idea to try to create some building blocks, like techniques, let's say, in a martial art, and then if you want to have your kung fu to be big, then you need to know all the techniques. In electronics, it means that the fundamental thing to be able to proceed with the circuit analysis and the circuit design is the study of the fundamental circuits. So you need to know all these theorems. There are some of them are more important than the others, let's say, because maybe you can use them more frequently, but the more you pay attention and you spend times on the fundamental circuits, then the bigger is your kung fu in electronics. So here you had an example. So at the beginning you see this and you say, what is this? Then you carefully inspect it and you say, okay, but the input impedance is infinitive, so I can break this circuit in two circuits. One which is the two resistor, the voltage divider, I already know and studied. The one is the operational amplifier, and I have a simple model for it, and then if I combine them together, then I get a new circuit, which is the threshold circuit, the comparator, and so on. Now let's try to introduce a different topic which is again an analog to digital converter, but implemented in a complete different way. and this way is called sigma delta. It's very popular, so basically nowadays all analog to digital converters are implemented this way. So let's see how it works. We have an input, so our variable, a voltage. It enters a differential amplifier implementing a summating node. So this thing has two inputs, the plus and the minus. So the output of this thing would be, let's say, a coefficient alpha multiplied V in plus beta multiplied this input, which is the output of this thing here. So here we will have a certain value. Then this value passes through a thing which is called the integrator, which basically is a low pass filter. So let's say that the signal here is a constant. Then if you integrate a constant in time, you have to summate this value plus the subsequent one plus the subsequent one, so it creates a signal that goes up like this or down according to the sign of the values present in this signal here. So if this signal is moving slow in time, we can imagine that it's passing through a value to another value to another value. You can think that at the output of this thing you will have a signal that we will increase, then it will decrease, then maybe it will increase again, then it will decrease. It will do something like this maybe. Of course, if you want to compute it precisely, you have to compute the integration of the input signal. And this can be implemented as a low-pass filter. But let's consider this thing just to have a qualitative description of it. Here we consider a constant signal. Here we have something that goes up or down. So this thing is fed into another building block, which is a comparator having a certain threshold that is in between the range of all possible values for this thing. So this thing will span from a V max, from a V min to a V max, and the threshold is something in between here. It can be 0, for instance, if V max is plus VCC and V minus is minus VCC. Okay, so when this signal, which is the result of the integration of this, is inside the circuit, this circuit is a digital comparator. It will produce a 1 if the signal here is above the threshold, or a 0 if the signal is below the threshold. So here you have either a 0 or a 1. Let's say that the signal here, according to the polarity of this segment of signal here, this little chunk of signal in time, is like this, and it surpasses the threshold, it produces a 1, then the 1 enters into this building block where we have a sort of controller switch that would be a relay. And for us, we know that it would be implemented as a transistor. So this thing controls the gate of a system which is made with transistor, and we've connected this output here to either plus a certain reference volt or a negative reference voltage. So if the one makes this switch to be switched to the plus, then here we have at the input B plus Vref, Vreference, and this thing is subtracted from the V input by this summating node with this negative weight here. So it means that this signal now becomes lower than this slope might become negative, and then if we had a 1 input, now this thing is not surpassing the threshold, then we have a 0, but the 0 is making the switch in this way, sorry. So then this signal this time becomes negative, and minus something becomes positive in this summation node, and then the signal at the output of this becomes this, assuming that we have the same signal. This loop can be very fast. So now we have again a positive slope. We have the signal here surpassing the threshold, so we have a 1, and so out of this node we have a signal which is like this: 0, 1, 0, 1, 0, 1, 0, and so on as the time is passing. So if we carefully study what happens at all possible values, we will see that the more the signal is positive here, the more the proportions of ones we will have in time. So for very positive signals we will have something like this: 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, and so on. And for negative signals, the more they are negative, the proportion will be reversed. So we will have something like 0, 0, 0, 0, 0, maybe 1, 1, 0, 0, 0, and so on. So this thing, this strange closed loop, transforms an analog signal, because this now can vary in time, into a sequence of a serial sequence of 0 and 1s, where the percentage of 1s versus the one of zeros is the representation of the voltage. So this thing is called sigma delta, because of this summation and maybe the difference in this differential amplifier. So this thing is very good for us, because basically the resolution of this converter depends on how fast this loop is. So if this loop is very fast, then this sequence of numbers is very dense, and the denser it is, the more possibility we have to represent let's say imbalance between the number of 0 and 1s in this serial sequence. So the resolution is it goes with the timing of this thing. And the good thing is that now we found a way to increase the resolution of these analog to digital converters, but the circuits is very simple, because we have only one comparator, so only 1 bit ADC. So if we don't want to build an enormous number of ADCs, but we can just build one but fast, and then we can still digitize a signal with a very high accuracy. In order to have the value of the signal, we have to wait a certain amount of time, which is the time for decoding this serial sequence. And the time is a compromise between the resolution we want to have in the amplitude and of course also how fast is the signal. So we can't wait maybe so much to have this signal decoded into a serial sequence, but we can try to find some compromise. Then this signal can be processed whatever to another with a digital circuit that, for instance, is able to put this into a memory and then decode this percentage of numbers into a binary number representing the value more appropriately. So this can be done with some combinational logic circuits. So we never have to underestimate what we can do with a single bit, because if the circuit is arranged in a clever way, we can still do a lot of things, even if we have one bit logic.